Hi, welcome to my channel, Theoretical Physics with Mark Weitzman. And today I just want to do a little blog issue on some stuff that I've been reading on for the last couple of weeks. And it's sort of like on mathematical physics, but more the modern mathematical stuff, which doesn't really appeal to me that much, but is important. And two of the books that I have here shown, like Gauge Fields, Knots, and Gravity by Baez, I've been reading a lot on, and also The Geometry of Physics. So this is sort of like modern mathematical notation. And what happened was I was watching this video by Jean Carroll. He's a very well-known theoretical physicist and expositor, and I think he's moved back east. I can't remember the name, somewhere in Pennsylvania, of where he's teaching now. He has a position in philosophy and physics. But he said something, which I'll play for a second from this video he has, which is just on Einstein's equation. But it was a very good, apt thing. It's sort of the way I feel, too. Just one sentence of it. So I'll play the video for about 30 seconds right now.
Boring. If there's one thing that mathematicians are very, very good at, it is inventing notation that makes unwieldy but understandable things into very elegant but impenetrable things.
So that's sort of how I feel. You know, a lot of this mathematical notation, it's elegant, but, you know, I prefer like the explicit tensor type of notation. But I'll talk about this book that I'm going to start reading, and I'll even invite some of you to read with me if you like. But this is from the preface. This book is very course in mathematics for students of Physics 1. It's an abstract way of teaching like first year linear algebra and calculus, but maybe goes to second year as well. It's not difficult, but what's interesting, like in the preface, he sort of shows you, what the idea is in the book, These are Maxwell's equations over here. There's 8 equations because you have 2 divergence equations, and then you have the curl equations. And this is how Maxwell would have written it. And then this is how, over here, we get down to 4 vector equations using traditional vector analysis. And this is how most physics students learn Maxwell's equations, either in the first course in freshman physics or in a second, more advanced course. And then below that, at least on the right side, this is where students of relativity and theoretical physics, this equation will be very familiar with, where we replace the electric and magnetic fields by a single anti-symmetric second-rank tensor, and we take its divergence and set it equal to the current. That gives 2 of the equations. The homogeneous equations over here, though, you may not have seen this using the Hodge-Star operator, but this is how they look there. There's another way to write them. I won't write them right now, but it's sort of like F alpha beta comma gamma plus F gamma beta, just cyclical of F alpha beta comma gamma. Comma, of course, means taking a derivative. So this is all familiar to me. And then this is how the mathematicians start writing it. The exterior derivative of F equals 0. Okay, I'm cool with that. This, though, is not really the way that even the mathematicians write it, or at least I haven't seen this notation. What I have seen is notation sort of like star or D star F equal J star, or something like that, or star D star F equal J, where star is, again, the Hodge-Star operator. Anyway, so that, along with, I don't know if you know it, but a few weeks ago, Chern-Simons, who's made, almost like $50 to $100 billion on Wall Street, and was originally a mathematician, and he's famous for working with the mathematician who was a real mathematician, a real genius, Chern, and they came up with the Chern-Simons form, and You can look at it here. This has applications in a lot of areas of physics. Basically, what I'm trying to catch up on is things like coordinate-free geometric ways of doing things, topological ways, looking at the topology and the geometry, exterior forms, and everything. So these are like Chern-Simons 1 form. And this stuff is all useful in quantum field theory. As you can see from the title of Baez's book, Knots and Gravity, it's related to knots. String theory, Witten did all this stuff with the Jones polynomial and knots and everything. And it's all related with gauge fields. It's all this modern mathematics. And it uses notation. Sometimes, I'm familiar with wedge products. That's no problem. But sometimes it goes beyond that. If you look at this thing over here, F equal dA plus A wedge A, that looks like a Yang's Mill thing or something like that. It's a little bit related. So I decided that I need to learn this stuff better. And I started reading. I read about a third of Baez's book, which I highly recommend, even though he's like sort of an in-between mathematician and mathematical physicist and theoretical physicist. So he's very good with all this stuff. And this book is like a relatively easy book, but it's written from a mathematician's point of view. It uses abstract notation as much as possible. So I got to like the de Rham cohomology. I don't know if I'm pronouncing this right and everything. And then I started getting lost. So I said I need to look at some easier books that I have or will have, and I purchased some. And this is, as I showed earlier, this book is a 2-volume book. The first one is very easy, but you can get these books for like, I got mine like for I think $10 online used, and it it looks perfect. It's not worn or anything. It's almost like brand new. So you can get, if you go to the you can get them new and they cost more, but if you go in the used and new, you'll see things like, you can get them hardcover for $5, It's just a question of what condition you want, used good. That's it's probably the one I would recommend there, but they're very cheap. These were published in like 1989, 1990, and they all get very good reviews. This is the volume 2. And so I'm going to get them both online. I'm waiting for volume 1 now, but I have volume 2. And volume 2 looks very, very interesting. It has a, let me see if I can go back to this thing. They have the table of contents. So if you look at the table of contents of volume 1, it's very elementary. Your usual linear algebra, but it does it in the more mathematical notation and everything. But eventually he starts doing differential forms and exterior calculus and line integrals and everything. But there's nothing great about volume 1. I mean, it introduces you to a more abstract notation. But volume 2 is very interesting, because he starts with the theory of electrical networks, and I couldn't think of anything which is more simple and boring, Kirchhoff's theorem, all this stuff. But he does it in a way where he does like the topology of one-dimensional complexes and bases and dual bases and cochains and the D operator. So he's really doing this electrical stuff to illustrate all of these like topological techniques. Then he has another problem, and he relates it eventually all to these things like dual spaces and cohomology and higher dimensional complexes. So this is a way to get an easy introduction to some topology that's needed in physics and used. And then he goes through, he does the star operator in Euclidean 3 space. So he gets you sort of an introduction on all these things. And here he has a whole chapter on the star operator, and he gets into Clifford algebras and everything. So this is all done in like, believe me, it's like sophomore level at the worst. I mean, it's freshman, sophomore level. Maxwell's equations, and then he has a couple interesting chapters on complex analysis and thermodynamics as well. So my plan is to start reading through this book. I have volume 1 in a PDF, but I want to, when the book comes in about 2 or 3 days online, I'm going to start reading this. And if anybody's interested, and there's a lot of problems in the book, if anybody's interested in reading along with this or doing this with me, I'll have a post up on my piazza course on the theoretical physics version. And, maybe we can work through it together. Usually no one wants to do it, but in case somebody's interested in it. I said volume 2. Now, a lot of this stuff, the first real good book on these things, and this comes from Differential Forms by Harley Flanders. It was published in '63. It's a pretty nice book, and it was republished by Dover in 1989. And you can, again, this is one approach to learning about the exterior derivatives. And let me get to the table of contents. It's mostly about exterior derivatives and the star operator and differential forms and, the applications in physics. But he doesn't go to all he does Maxwell's field equations, but he doesn't go to all the really advanced stuff in quantum field theory and everything. But he covers a lot of this stuff. It's in an old-fashioned notation and everything. This book was mentioned in Meisner, Thorne, and Wheeler as being like a little old-fashioned, but it's a good book, actually. And that's one place where you could start. That's a classic book. This is on the website. It's, you can get it for like $9 in paperback and everything. I think I'll get this, as a matter of fact. Anyway, that's differential forms. As I mentioned, this is like Meisner, Thorne, and Wheeler. They have, if you look on their general relativity gravitation book, if you look at the table of contents, this will be really hard to see, and I can't magnify it, unfortunately. But they have a couple of chapters right off the bat on electromagnetism and differential forms. So you get the differential forms point of view and a little bit of differential topology also, one forms and tensors in Meisner, Thorne's Wheeler book. So that's the first place I saw it when I first read MTW in 1973 or 7 when it first came out. So also, okay, Jean Carroll, who we saw earlier, he's got a very good gravity book, graduate level space-time and geometry, but he too has a nice couple of chapters where he teaches, the dual vectors and the one forms and everything, although for the most part he sticks to tensors, but he does do one forms, and he does have a chapter on sort of like differential geometry with manifolds and everything, differential forms, and so on. And he also has, at the end of the book, he has a bunch of appendices where he talks about manifolds and diffeomorphisms and Lie derivatives, and so that's good stuff too. So I like his general relativity book as an excellent place for someone who's like advanced undergraduate or graduate level to start. Another book that I have that I read a long time ago, which was actually Meisner, Thorne, and Wheeler in their gravitation book recommended, was Tensor Analysis on Manifolds. And again, this is sort of like, your usual math, where they do the whole, it's a little bit more rigorous, the whole topology and manifold definitions, and then the whole tensor algebra, and they do, they do the forms too. They do the exterior algebra as well, bilinear forms, Hodge duality, that's the Hodge-star operator, and symplectic forms. But it's a lot of mathematics, not much physics in this, a little bit at the very end. They do some Hamiltonian manifolds. This is the book that I recommended that I talked about earlier. It's not difficult, but it's got, I can't show you a sample here, but not too expensive. You can get it for $36 paperback. You can get, maybe they got used ones that are cheaper, not that much cheaper. But this is sort of like, will get you started. It goes up to like loop quantum gravity. It gives you just a basic introduction to like where that came from with the new variables, Ashkatar variables, and so on. Another book, this one has a lot more applications in physics eventually, but it's sort of like less abstract than Baez's book, but mostly covers the same material. It's about 700 pages, and it covers all the things with differential forms and manifolds, and just go through it. But it has a few Lie derivatives. It has a bunch of chapters on groups and manifolds and geometry and topology that are very, very good. And he even has a couple of chapters where they do some real physics, and he goes into the advanced stuff. These are the things that I want to learn, which I don't know right now. I've heard about them, but I don't really know things like Betti numbers and de Rhams theorem and harmonic forms and the Chern-Simons forms, and I'm familiar with fiber bundles and topological quantization, but there's a lot of things I need to learn on these things. And he goes through the whole Dirac and Clifford algebra, and he has a nice chapters on Yang-Mills, and he does all that stuff with the Yang-Mills equation. So there's a lot of math and there's a lot of physics in this book. The style, it's not the greatest read. Some of it is very boring, and a lot of it is repeated over and over again. But it's something you might want to look at. Another book, this is even more advanced, Geometry, Topology, and Physics, second edition now. This has some physics in there, but mostly it's math, and it's sort of just a lot of definitions, not that much calculations. That's what bothers me about these books. A lot of definitions. He starts in the beginning with a couple of nice chapters. Chapter 1, quantum physics, but then he goes back to the mathematics, and it's just, one thing after another. But there's a lot of stuff I don't know in here, like the homology groups and everything. I don't want to learn this from this book, but I do want to learn it from that Harvard book, Course in Mathematics for Students of Physics. Anyway, these are the table of contents for Nakamura's book. And he's got a little bit more physics in there, here and there. But mostly it's mathematics, a lot of definitions. But he has these anomalies. That's very important. And even a chapter on bosonic string theory. Finally, this book I've had a long time, but I've only read like about a third of it, which is on knots in physics. And interesting thing about this book is a lot of pictures. But eventually it gets related to the, apparently he's in the 4th edition. I'm not sure which edition I have. I probably have the 1st edition. But anyway, he starts with a short course on knots and physics and goes to things like the Yang-Baxter models, Alexander polynomial. I've heard of all these things. 3-manifold invariants from the Jones polynomials. I don't think it's all that rigorous, but he covers a lot of interesting material. And there's a lot of pictures in the book on knots and how he... It starts with knots, but then he goes into a lot of other things, crossings and things like that on how to get it. So this is also an interesting book. So that's where I'm at right now. I'd love to read all these books, but for the most part, I want to start with the easy books, Course in Mathematics for Students of Physics, and then read Frankel's book, Geometry and Physics, and then go through the gauge fields a little bit more carefully. and eventually get to the point. There's all these topological methods in quantum field theory. A lot of quantum field theory books, you'll see a chapter or two on it, but they're not that easy to understand unless you have the mathematical background. So that's all I wanted to do today. And as I said, I'll have a post up on my Piazza site on topics in theoretical physics. And I'll see you again next time. Thank you for watching.